Thank you for watching the National Atomic Testing Museum, March 2nd, 2018 Distinguished Lecture Series. The Kilopower Project and the Future of Nuclear-Powered Space Travel. Presented by Patrick McClure.
Thank you. So just real quick, I'm gonna make mention of all the wonderful people who work on this project. So the project is actually funded by NASA for about 75%. About 25% of the funding has come from the NNSA. We have Glenn Research, NASA Glenn Research Center in Cleveland, Ohio, who is our lead. We also have gotten support from Marshall Space Flight Center in Huntsville, Alabama. In addition to Los Alamos, who we've had a lot of great work from folks both here in Las Vegas and back in New Mexico. We got our reactor core from the Y-12 facility in Oak Ridge, Tennessee. The folks out at the site, who is now, and I'm going to hope I get this right, SMTS, did I get it right? Yes. Used to be NS Tech, have also been extremely helpful, as well as all the federal employees here. So what I'm going to do is actually, again, we are going to talk about Kilopower. Kilopower is a very small reactor for space applications. That's what we're going to discuss. I'm going to get you started, and I'm going to ask you to bear with me because I want to get a video up from you. NASA Langley did us a nice video. If you like the video, it's actually up on YouTube, but I think it's a good way to start as an introduction. So bear with me. We'll get it going here, and we'll watch the video together.
NASA is advancing an existing technology to enable future space exploration of the solar system. With plans to expand human missions to Mars and science exploration of the outer planets, the need for reliable power becomes essential. Space-qualified nuclear reactors are one technology that can provide for safe and reliable power for many of these missions. Nuclear power in space is not new. These clips from the 1960s provide a window into the past. A U.S. program was put into place that developed and flew the world's first space reactor. Before the reactor is turned on, that is, prior to fission starting, the reactor fuel is very safe and only mildly radioactive. A joint venture between NASA and the Department of Energy is underway to develop a new space reactor that meets a range of exploration missions. The reactor, called Kilopower, can deliver a range of 1 to 10 kilowatts of electricity. That is enough to power anything from one toaster to an entire household. Kilopower will be tested in the Nevada desert at the Nevada National Security Site. The test has a fissioning reactor deliver heat to Stirling converters. Each converter produces about 100 watts. The goal of the test is to confirm the system's predicted performance. The reactor core is a cylinder of enriched uranium that is 6 inches in diameter. A beryllium oxide reflector will surround the uranium core. A single rod of boron carbide is used to turn on the reactor. The reactor uses well-established nuclear physics to self-regulate the fission reactions, and this feature eliminates the need for a complicated control system. The reactor uses nuclear fission to produce heat, which is delivered by heat pipes to power generators, known as Stirling converters. A radiator is used to keep the Stirling converters cool. A great deal remains to be done, but with the successful completion of the nuclear test in Nevada, NASA is coming ever closer to the reality of a space-qualified nuclear reactor. Over the coming years, the reliability and safety of Kilopower will be tested to assure that when the new era of space exploration begins, all systems will be a go.
All right, thank you for helping me watch the video. So now, I've done this talk a couple of times, but typically it's been to folks at the laboratory at NASA. So I actually had some folks at the laboratory look over it, and they thought I needed to do a little bit of definition. So this is the Wikipedia portion of my talk, so please bear with me if it seems like I'm telling you things you probably really already know. So the first question usually you get asked is, why do we care about using nuclear power in space? So what I did was I tried to actually put some bars in yellow to give you an idea of the relative energy delivered by sunlight to the various planets. And so what you can see is solar power works great for the Earth, especially in low Earth orbit. We can get a lot of power. As you get to some place like, well, let's go to the moon. As you get to the moon, there are shadowed portions of the moon. There are some deep craters we're interested in. In addition, there is the lunar night, which lasts 2 weeks, where you don't have sunlight. As we get to some place like Mars, you still get quite a bit of sunlight, but Mars experiences some fairly extreme dust storms. These can actually last up to 2 years. So because of that, we have to have a power source that can operate continuously. And so actually the very first group that got interested in our small reactor were the folks that are planning Mars missions. The idea of a continuous power source that was very reliable was very attractive to them. As you move out to the planets like Jupiter, Saturn, and the icy giants of Uranus and Neptune, you start to lose enough sunlight that you can't use solar power out in space. So nuclear is your only option. So what we've done for the last about 30 to 40 years is we have an isotope of plutonium, plutonium-238, which is a heat source, and it provides a very nice power supply that has been used to do, say, some of the missions like Voyager, Galileo, Cassini. New Horizons was recently the one that went to Pluto. The issue there is it's only about 100 watts of power, and I'll try to put some of that in context here shortly. But we're also starting to run out of plutonium. It was a byproduct of the weapons program, and since the Cold War ended in 1989, that's put a little bit of a stress on the system. So with that, okay, now let's just give a little couple of definitions. So we are talking, when we talk about this reactor, we are talking fission. Fission is what you think of when you think of a nuclear power plant. We split an atom's nucleus by a neutron. If we have enough fissional material present, we can get what's known as a chain reaction that can be self-sustained. And that self-sustained chain reaction is known as a critical mass. And so when you think about this small reactor, we have enough material there to make it go critical and produce heat. We're going to talk a little bit about that because one of the things we get to keep the material amount down is we can surround the reactor core by something that will reflect those neutrons back in. Second thing you're going to hear me talk about tonight is a heat pipe. Heat pipes were actually invented at Los Alamos in 1963. We're also going to talk a little bit about the Rova-Nerva project, and this was actually a technology out of the Rova-Nerva project. A gentleman named George Grover, who was one of the group leaders at Los Alamos in the reactor design group, he and several other people invented a heat pipe. It's really just a small sealed tube. It's got a little bit of a liquid in it. And that liquid will boil at the hot end and it will condense. It will move at the speed of sound to the cold end where it will condense. And that is a really efficient way to move heat energy. We then use a wick to bring the fluid back to the hot end. So the nice thing about that is a heat pipe will work in any direction. It will even work against gravity. So if you're someplace where there is no gravity, it's a great way to move heat. Heat pipes have become ubiquitous. They are everywhere. If any of you own a laptop, it's got heat pipes in it. They're just about any electronic you can today has heat pipes. So they're pretty much a daily part of our life at this point. Next thing I'm going to talk a little bit about are Stirling engines. Stirling engines actually are a device that were invented by the Reverend Dr. Robert Stirling. I think like in the 1700s. They are a nice way to take something where you've got heat at one end and you can remove heat at the other, a cold end, And with that, you can either do mechanical work, or if you attach, you take and you move a magnet through a coil of wire, an alternator, you can actually produce electricity. And so what you see on the right is a modern Stirling engine. Again, they're used quite a bit. If you were to go to a lot of places for like the International Space Station, they use Stirling engines as cryocoolers to basically keep things like hydrogen or helium and some other liquids very cold. So I'm going to talk about that because now I'm going to talk to you about what is Kilopower. So I've told you Kilopower is a small reactor concept. It actually will range in power, and I'm going to show you here in a minute, but I want to point out the pieces of it. So Kilopower has a reactor core. It is highly enriched uranium. At the low end, it's about 30 kilograms. At the high end, it's about 50 kilograms. It's surrounded by a neutron reflector. This is beryllium oxide. And again, what that does is it means that when we surround it by beryllium oxide, we need less nuclear material to get a critical mass, which is nice. That keeps our weight down. There is a single rod of boron carbide that turns the reactor on and off. The reactor itself will actually run itself. It will change its power level depending on how much power is required from the power conversion system. So above the reactor is shielding in the concept you see for flight. Above that, you will see that there are heat pipes traveling up from the core to these Stirling engines. That's how we get the heat that the core produces to the Stirling engines. The Stirling engines are cooled by that radiator. That keeps the cold end of the Stirlings very cool. And by having that temperature difference, those little Stirling engines will make electricity. Now, what we're testing at the test site, you see what would be on your left-hand side. We're not testing everything. We're not testing the radiator panels, but we are testing the reactor core. We have our neutron reflector. We have our heat pipes and Stirlings. And so we are moving very rapidly here. In almost 3 weeks, we will use that little reactor to make electricity with those Stirling engines. So when we talk about, I was going to tell you about power. So when we talk about how much power does Kilopower produce, at the low end, it will make about a kilowatt. That's about enough to power your toaster or your blow dryer. It's not a lot of energy, but keep in mind it's 10 times more energy now than NASA has on most of their missions. So if you looked at New Horizons, went out to Pluto, it had about 100 watts. If you look at Curiosity on Mars, it has about 100 watts. So if we gave NASA a kilowatt, that would be 10 times more power than they're used to. Now your home at peak may use 5 kilowatts. If you had your air conditioner running, your refrigerator, your daughter was using the blow dryer, and you were maybe doing a few other things, you might get your house up to 5 kilowatts. At the upper end of power that little reactor would make, which is 10 kilowatts, that's enough power for several homes. And actually what you see there is that would be either for deep space missions as well, but also that would be power we might put on, say, the moon or planetary surface like Mars. Okay, so what are some features about this reactor? Well, first of all, it is very simple. It's about the simplest reactor you can make. We like the fact that it can be scaled and power with the same components. Those heat pipes are very reliable because they're passive. There are no pumps or loops like you might see in other devices. Stirling engines we like because they're very efficient. They convert about 25% of the heat generated into electricity. That solid uranium metal fuel can actually be made at an existing DOE site. That's why we had Y-12 involved, was they can make that fuel for us. They can do it with no changes to their facility. And for instance, if we want a lot of Kilopower reactors, we would just go have them make us reactor cores and set them on the shelf. And that's nice because then when NASA wanted something, all we would have to do is pull one off and go build the reactor up. This is a very low thermal power reactor, so there aren't a lot of radiation effects to the fuel. That kind of helps to keep testing at a minimum. To only start it up, all we have to do is pull out that boron carbon rod. Sorry, I'll get it there. So that means we have to have a small battery to start it up and to shut it down, but that's not too bad for everything we're doing. The reactor can be started and stopped. The idea there, and we'll talk a little bit about it, is if you had one on Mars, there's some desire by NASA to maybe move them around. They've thought about using them to power rovers, and we'll talk a little more about that. You kind of saw that in the video. So there's some idea that we might actually move them around. Again, the reactor itself is self-regulating, so not a lot of electronics to have to worry about to keep it running. We think in terms of what it's going to bring to NASA is it's going to be low cost. We'll talk some about safety. The reason they're very safe is because we're not going to turn these reactors on until they get where they're going. So it's just a little bit of minor radioactivity in the fuel. This actually, again, for NASA's sake, it really does provide them more power than they're used to, and that allows them to use them in extreme environments. And also they could, and we'll talk a little bit, maybe use this for electric propulsion in the future. So how big are we talking about? So I've got a model over here, but if you want to think about how big Kilopower actually is, at the 10 kilowatt level, the reactor core is about the size of an oatmeal box you might have in your pantry. The reactor with the reflector and the shielding is about the size of a trash can. The whole thing will be about as tall as a very tall stepladder. That's what we're talking about. Now it weighs quite a bit. That would actually weigh about 1,800 kilograms, and that's actually with full shielding that we might have now for, say, a Martian visit. So how do we get NASA? What are some of the things NASA has thought about? Again, we really very early on got them interested, a lot of interest from the folks that are doing the Mars work. In addition, they've talked about lunar applications. It could be used for orbiters or landers. There's a lot of interest in NASA in going out to the gas giants and their moons. Things like Europa, Titan, and Enceladus. They would especially like to land on them if we could do that. I told you this thing could be used for nuclear electric propulsion. Right now, if you look at most of the spacecraft we send out into space, for instance, for Pluto, we had to fly by it because we didn't have any power to slow the spacecraft down. With a 10 kilowatt reactor, we could actually put on electric ion thrusters, and you would travel halfway to Pluto at one speed, then you would turn the spacecraft around and you would actually slow it down so that by the time it got to Pluto, it was moving slow enough and it could actually go into orbit. There are some potential other missions. If for instance Elon Musk makes it to Mars, we could power colonies. If someone actually wants to go mine the moon or an asteroid, I guess down the road those are also potential uses. Let's talk about the Mars surface just a little. I told you, right now NASA is used to things like 100 watts. The new rover that's going to go up will only have 100 watts. But if we want to put people on Mars, we're going to need a lot more power than 100 watts. So I'm sure most of you have seen the movie The Martian. Have most of you seen that movie? So if you remember at the very end, Matt Damon wants to get home and he has driven his rover, and there is a vehicle he is going to get in that is going to take him from the Martian surface back up into Mars orbit so this spaceship can come pick him up. That's the exciting part of the movie. I won't give it away, promise. And that's where we come in. In order for that ship to get off the surface of Mars, it needs propellant in the form of methane and liquid oxygen. What we're going to do with that reactor is we will have a unit that would actually take CO2 and, for instance, turn that into liquid oxygen and store it. So the reactors would actually arrive on Mars long before people would. And so I'm going to show you another slide here, kind of illustrate this. So long before people get there, the what's known as the Mars Ascent Vehicle would actually already be there. These little reactors would be moved and turned on robotically, and they would make the fuel to get our astronauts off the Martian surface and back into orbit. Once they actually arrive, we still need electricity. We actually don't need 40 kilowatts at that point. We only need about 15 kilowatts. So some of the reactors would be used to power the habitat, and that would be to make oxygen to purify their water. The other reactors would potentially be moved around, and they would provide power for the rover that you see up on the right. So they would be like Tesla charging stations on Mars. So you would have them out, and they would do things. So by the way, another thing about the Martian, they show you all the solar panels, except that they don't tell you that they really need 10 times more than they actually show. So just a plug there for nuclear. And so again, the idea is we wouldn't send one reactor, we would send 4 or 5. Okay, I'm going to give you a little history here because now we're going to turn to what we're doing today. And so as you guys know, being in Vegas, a lot of this has to do with the fact that we really like the test site. It's a great place. It has a lot of history that has to do with space nuclear power, and in particular, there was the Rover Nerva project that was, had a long history out at the site. And of course, now the difference is these were actually for propulsion. So our little reactors are to produce power. These big reactors were, and they were some of them the most powerful reactors ever built, were used to, we were going to flow hydrogen through that reactor core, and that would provide thrust like a rocket would have. Now, a lot of the design and testing was performed at Los Alamos on critical experiment machines. Those same critical experiment machines live today, and that's actually what we're testing Kilopower on today. And so this was a great program, and it was a forerunner to some of the stuff we're talking about today. Now, when we talk space reactors, the U.S. has actually only flown one space reactor, and that was in April of 1965. It was called SNAP 10A. Actually built, the company that built this was in Santa Souza, California, Atomics International. They actually sent the reactor up and actually started to run it, but it was attached to a spacecraft called an Agena. It had a voltage regulator failure, and when it did, it sent a signal to the reactor to shut down. And so after 43 days, the reactor shut down. And how it shut down is, what you can't see up there is it had a little explosive charge. And that neutron reflector that I was talking about, they had those as well, but it blew those off, and so the reactor couldn't be restarted. So it was boosted to high orbit, and it's still there today. But it is our one and only space reactor flown in the U.S. I should mention the Russians flew about 30 or so. They flew these up to around 1988 or 89. The Russian reactors were for spy satellites. SNAP 10A was also going to be for a spy satellite. That was their original application. And that was, the Russians, I know you guys had a talk on Operation Morning Light not too long ago. It was one of those Russian reactors that actually was turned on, came in hot, that actually caused some problems. So how did we get here? Since we've had the SNAP program in 1965, we've actually had a lot of programs to try to build a reactor, but none of them have really ever been very successful. As we were talking about how to get this restarted, what we realized that most of those programs were very complicated, they were very costly. One of them cost a little over $1 billion. One of the ones we just had a few years ago, we spent $400 million on. A lot of it was sort of how we were managing the project and what we were trying to build. So we took a new look at it. I'm going to show you how we got NASA interested. We actually, in 2012, did a test out at the test site as a kind of a proof of concept test, and that got NASA enough confidence in us that they actually gave us the money to go build and test this reactor. But instead of spending hundreds of millions or billions, we've spent less than $20 million. So for us, we think it's a really a great win, and to show folks we can actually get something done and not really break the bank. So I was talking about we actually had a test that got NASA interested in what we were doing. We called that test DUF, or Demonstration Using Flat Top Fissions. Flat top is an existing critical experiment that lives at the test site. You see it in the upper right-hand corner. And the circle I have drawn around is actually a plutonium core, but we have a uranium core for flat top. And we took that uranium core. It just so happens to have a 0.505-inch hole that goes through the core. And we actually stuck a heat pipe in that. We attached it to a couple of Stirling engines that we borrowed from NASA, and we made 24 watts of electricity. I know it doesn't seem like a lot. Yeah, yeah. But we lit up a light, and actually that was the first heat pipe cooled reactor ever built, and we showed it could be done. And so that gave NASA a little confidence in our ability to get things done. So I'm going to show you a little better picture of what the experiment looked like. Our little reactor core is inside that big hemisphere on the far left. That's a reflector that actually makes things go critical. It's hard to see the heat pipe, but it's there. It's right in the center. And then all of the gizmo on the right was the Stirling engine that we used to make power. And we did this test for around $700,000. So, and we got NASA actually out to come, some NASA management to come out and see it. One of the reasons we like this reactor concept, I won't spend a lot of time on this because I'm going to have to redo it. I think it's a little overly complicated, is this reactor will respond to the power that's demanded from it. So if I change the power that the Stirlings say that they want, my reactor will change temperature, and based on that, it will change the reactivity and the amount of fission power it generates. What's nice about that is, let's say in space I have all these Stirling engines, but one of them decides to break. If a Stirling breaks and it changes the amount of power that the unit can then put out, the reactor will respond to that, and it will only provide the power that's being asked out of it. So why do we like this design? Well, first of all, again, it's pretty simple. It's pretty basic. There aren't many parts. It's not complicated. We can make everything we need to do with existing infrastructure. That was one of the lessons we learned before, was we had this tendency to devise programs where we would then go ask Congress, well, hey, I got this reactor I want to build, but I need a brand new billion-dollar facility to make it work. And so this time we decided, well, let's not do that. Let's test where we can, and let's make sure we have facilities where we can get fuel and do those things. Again, we're big fans of heat pipes. They're simple, they're reliable, they're robust. And our final goal was to take advantage of the test site since it existed, and they had all these cool facilities. That would help us keep testing and demonstration very low in cost. So with that, I do want to talk just a second about space reactor safety. Until that reactor is turned on, and until it undergoes fissions, there really isn't much radioactivity in the core. So my little 1 kilowatt version has about 1.5 curies of radioactivity. I know it's hard to judge what that is, but I'll give you a thing to adjust it to. My 50 kilowatt or my 10 kilowatt version has 2.5 curies of radioactivity. The current radioisotope systems we already fly have about 60,000 curies of radioactivity. So if something bad happens to my reactor on launch, we're really not going to have any consequence to the public. So if something bad happens, we expect doses to be far less than 1 millirem, and that's maximum dose. And to give you an idea, that would be your yearly dose is about 300 millirem. So it'd be less than something that would happen, say, if you took like a 4-hour airplane flight. Now, once that reactor has fissioned, it does become pretty radioactive. So all our goal has been to avoid doing anything in Earth orbit. We don't plan to use these reactors until we get in deep space or until we're on a planetary surface. So we think they're going to be very safe. This is one that NASA always wants me to show, is that for the work we're doing right now, we're following all the rules, right? We've done everything we're supposed to do, and I don't want you to read all that, it's just too much there. But we're doing everything like we're supposed to. All the National Environmental Policy Act, all of the regulatory safety that we're doing currently is all up to speed. So let's talk about what we're doing at the test site. So we had this flight concept, but we are actually testing what you see sort of on the second bullet there. That's actually the core, the heat pipes, and the Stirling engines. So what we did to begin with is we actually, up at NASA in Glenn Research Center, we electrically heated that core so we could test the heat pipes and the power conversion. And we did that over a series of a year, and actually we did make some changes. We learned a lot, and we did all that before we brought it to the Nevada test site so we could actually do our nuclear testing. And what we're doing now, and we started this in November, is we've actually been doing the nuclear testing. And let's talk a little bit about that. So I want to show you what we're testing. These are real pictures. You can see on the far left, that's our uranium core. It comes in 3 pieces. That was what was shipped out from Y12 to the site. When we assemble that, and you can actually see the guys assembling it down below, that's the heat pipes attached to the core with some reflector pieces on top and bottom. What you see in the center is the actual beryllium oxide reflector as it's stacked up on the test article, and you can see some heat pipes and Stirlings from the power conversion system. And this is what it looks kind of mocked up. We actually had this over at Palace Station. We just had a conference. It ended up weighing about, we were going to try to bring it, but it weighs about 450 pounds. So we decided it was a little on the too large to bring over. But you can see the mock-up of the core, the heat pipes, and the Stirlings, but it stands about this high. So again, not super big, but that is actual size, and that is actually what we're testing looks like. So our test is called Krusty for Kilopower Reactor using Stirling technology. That's a series of tests. What we get out of this is we're going to ensure that how we've modeled this and designed it, that this reactor actually does what we say it's going to do. And we're going to do that in what NASA calls flight-like conditions, meaning that if we were in space, it would be in a vacuum. We're at the right temperature, we're at the right, everything does just like we say it will. And this gets us a lot of experience so that we can possibly move this forward. So let's talk about what we're doing. So in November, we began running tests where we only go up to room temperature. That means we get just right at the critical mass. We are critical. It's called delayed critical. We do that because we get a lot of great information. We did that through November and December. We did that with just the core and the neutron reflector. We then assembled the whole unit. We did that right after the new year. And that was, we added the heat pipes in the power conversion system. And then we again did all these critical tests. We have just finished those up. So going into March, we're at the last 2 stages. We are going to do what we refer to as warm criticals, which means we are going to start now bringing the reactor up in temperature. So we have 3 low temperature tests. The first one, we're going to bring it up about 100 degrees C. The next test, we'll bring it up a couple of 100 degrees C. Then we're going to bring it up to about 400 C. And from each of those tests, we gather data. We put that back into our computer models. And we say, hey, is the system doing everything that we believe it is? Which brings us to this last test, which is where we actually are going to bring the reactor up to full power, to its operating temperature, and then we're going to run a series of experiments based on this last test. By the way, right now that is scheduled for March 19th. So this is what it's going to look like after we get it up and it's stable. We're going to actually show that the reactor does what we say it's going to do. We're going to turn off some Stirling engines. We're going to change their strokes so that we draw more power. We're going to change their strokes so they draw less power. When we turn off a couple of Stirling engines, we can simulate what would happen if a heat pipe failed. Our very last test, again to show fault tolerance, is we're going to turn off all heat removal from this reactor. Now normally that's, people think, wow, you're turning off all the heat removal. Well, this reactor is so well behaved that it's going to go up about 30 degrees in temperature and it's just going to stay there. reactor core doesn't melt, nothing bad happens. And so we're going to demonstrate to NASA that, no matter what happens, this little reactor will be well behaved and do everything that we say it's going to do. So it's going to be very fault tolerant. We're hoping we get really good data from this. And so when we're done, that will be the end of the test. And we think we're going to have learned a whole lot of stuff. So just so you show you that there are real folks right now. This is actually a picture from last week. So those are Los Alamos and NASA scientists and engineers actually out to site putting the test article together, getting ready for this last set of experiments. So the big question is, okay, all that's really well and good, but what are we going to do next? Well, when we're done, in NASA terms, they say that we need what's known as a technology demonstration mission. Remember that for a lot of, before we would ever let humans depend on this, we have to prove that it's reliable and it's safe. And so lots of things have been discussed. I will tell you the things that have been discussed the most are things like a planetary flyby has been discussed. That means we would actually take the reactor and we would fly it past something like the moons of Jupiter. A Pluto orbiter has been discussed. An interstellar mission has been discussed where we just actually take the reactor and just like Voyager, we send it out through the solar system into deep space. I would say the mission that has got the most attention is possibly landing the reactor on the moon. That is because the new administration has said the moon is a priority. There are also private companies, in particular Blue Origin, Moon Express, I think Orbital, that have expressed interest in building moon landers. In particular, if you look at the one that Blue Origin has, it can take 4,000 kilograms to the surface of Mars. With the recent flight of Falcon Heavy and the soon flights for the Blue Origin rockets like New Glenn, this now seems like it could be a possibility where a rocket and a lander would be available to take our little reactor to the moon. So now the question is, why go to the moon? So one of the things they would like to do is the same thing they would like to do on Mars. They would like to find light elements like water or hydrogen. So the idea is the poles of the moon, particularly Shackleton Crater, they're very deep, they're very cold, and the thought is that that might be a place where you could find water. So in this case, they might fly the reactor to the moon, land it inside the crater, leave it on the lander, and then they would do a series of experiments to see if they could find water. So it's kind of like prospecting. Matter of fact, they've had many ideas to do that. And if we got that program, there are a lot of things that we still have to go off and do. We've never built the mechanism to start up the reactor yet and tested it. We would have to do some safety analysis for launch approval. There's a lot of what I call shake and bake. They have to actually build all the flight hardware and test it for launch loads. We would also have to figure out what it's going to fly on, and if it were on a lander or if we built a spacecraft, and then how we would integrate that in. So that's what's potentially next. Like I said, I'm not kidding. When you get to talk to your congressman, tell them you think it's cool, and make sure that they would actually hopefully put it into NASA's budget for the future. So with that, my last slide is how cool would it be if we had a moon base and we had several small reactors powering the moon base. Like everyone else growing up through the Apollo era, we thought we'd already be there, but for that next generation, that's still a reasonable thing, and hopefully we can make that happen. So with that is the end of the lecture portion of my talk. But I think we have time, and I'm going to ask, I'm assuming we have time for questions.
What's the lifetime of this reactor? What do you anticipate?
Good question. Good question. The question was, what is the lifetime of this reactor? In general, it's about 10 years. That's what we sort of tell NASA that we would kind of guarantee it. The reactor itself will go decades, if not longer. The Stirling engines will probably break first. So But I like to look at them and go, because I was telling somebody earlier, it's a tremendous waste of uranium. We're barely using the fissionable material in the uranium. We have to have that much to actually make it go critical, but we're really not taking advantage of it.
Is there an alternative to the Stirling engines that might last 100 years, 200 years, 500 years?
So thermal electrics are much more robust, but their efficiency is horrible. It's like 6%. So your reactor gets really big, and that kind of defeats our goal of a low thermal power reactor. And besides, we just think it's time to change. The Stirlings, if you look at NASA, they've got some that have run decades. I think they're good. They just need to get them in space.
How much uranium do you use, and what's the ratio of 235 to 238?
Okay. So at 1 kilowatts, about 30 kilograms. At 10 kilowatts, it's about 50 kilograms. It is highly enriched, which means it's 93% U-235.
I have a question about scaling. In the future, would you see scaling it up power-wise? And if so, is Stirling still good?
It probably doesn't go well beyond 10 kilowatts electric. There's a thing when you, this is a metal fuel. Metal fuels don't like to burn up very well because they tend to, every time you create a fission, you create fission gas. At a certain level, they will swell, and we're trying to avoid that completely because then you have to do a lot of testing, and we've decided testing is just too expensive. So we've picked a range where we can say we don't have to. So the answer is probably not. We would probably choose a different fuel.
Have you ever tested it in a thermal vacuum chamber?
So the question was, have we tested in a vacuum chamber? So both the electrically heated test and the nuclear test are in a vacuum chamber. The radiators, by the way, have been tested in vacuum chambers as well. In fact, the radiators have actually been tested on the International Space Station. So, have not tested the whole assembly. So, again, cost is kind of an issue.
Two questions. One is, if you ran this reactor for 10 years, you're going to have a lot of fission products. You're going to have a lot of poisoning, like xenon. So the question is, how do you accommodate that? Plus, at the end of 10 years, you got a lot of residual heat. So how much does it rise until you can you still control it if you lose the heat pipes at the end of 10 years?
So the question was on fission product poisoning. It's a fast reactor, so that's like xenon poisoning is not nearly an issue. But it will be radioactive. There'll be some fission products that are kind of at a steady state. When it's done, on the 1 kilowatt version, you're talking a decay heat after a few hours because it's got a lot of thermal mass of about 45 watts. At 10 kilowatts, it's going to have about 450 watts of decay heat. So it doesn't have a lot of decay heat. Unlike a big reactor, this one's going to be able to basically radiate that heat away. It really isn't going to have much of a problem. In other words, it's never going to melt. I'm assuming is the question you're asking. It's a fast reactor because the neutrons are at that speed. It's not because it's plutonium or uranium. It's just the physics. These are very fast, high-energy neutrons. They're not slowed down by a moderator.
What are you going to do with waste radioactive products once the reactor is done with them?
So it's a good question, is what are we going to do with the reactors when we're done? So they're going to be hard to get off Mars or the moon. So NASA has a container that we are going to put them in, and they will be flagged, I would assume, until there becomes technology that would allow us to get them home or do something else with them.
Just wondering if the Russians have something equivalent to this, or are they interested in this concept?
So the question was Russian interest. Well, the Russians flew their own set for decades. They have not shown much interest lately. I think they've got interest on other things. Although they have, I would tell you, great guys that can do stuff. The Chinese seem more interested than anyone else at this point. And it's very clear that they have a fairly active program.
So 450 pounds sounds like a heavy object to be launched into space for a power system. How does that relate to the RTG and weight to electric production ratio?
So the question was weight. On the 1 kilowatt, we're actually we're probably less than 400 kilograms. We're about 350. And an RTG only weighs about 40 kilograms. The nice thing is rockets are getting bigger. The lifters are getting bigger. And again, it's like a lot of things, I think it will depend on the mission. There are certain landers where I'm absolutely convinced they will only use RTGs. But remember, we don't have as much of that as we used to. So for some missions, it will probably be easier and better to go reactors.
What considerations have you used for, or instead of using solid uranium, some kind of uranium in liquid form?
Well, the only way I know to get a liquid core would be you could dissolve it in like molten salt. The problem with any kind of molten salt or liquid metals in space is, remember, it's really cold, so they tend to be solid anyway. So, for instance, when we did the one reactor I showed you, SNAP, which had liquid metal, you actually have to put heaters on the system to heat that metal up so that you can actually flow the liquid before you start the reactor, which is one downside to some of those designs. It's one of the reasons we like heat pipes, because I don't have to heat anything up. As I turn the reactor on, the heat pipes will automatically melt the material inside, just due to the natural way the heat pipe works in the physics. So liquids are tough in space, so especially because, again, they freeze.
So there's an element of risk of launching an RTG at launch time, in case there's an accident. How would you say is the comparison between that risk and launching this?
So the question was comparison of RTG risk to, I'll get back where the camera can find me here, versus the reactor. So RTGs, I told you, have about 60,000 curies. I am one that believes that RTGs are very safe. It's why we've flown them for decades. And how they achieve safety is RTGs are packaged very robustly. They have multiple layers of very strong material, very heat-resistant material, so that if the reactor or if the rocket blows up or if it catches fire, the material inside is not released or damaged. A reactor does, so that's one way to achieve safety, is to protect it. The other, classic way to obtain safety is to remove the hazard. And so with a small reactor, we're essentially getting rid of the hazard. We've went from something with a lot of curies to something with almost no radioactive component to it. It's there, but it's very minor. So from our standpoint, just what we're launching is just not that dangerous. Just of itself, if something bad happens, we don't expect consequences from that that would harm the public. All right, well, thank you folks for having me. I really enjoyed it.